So today we're looking at similar solids. So before we were looking at similar shapes. So we started off, the first chapter was like different shapes like squares, circles, and then we had a chapter on just like similar triangles. But now we're moving into similar solids. So with the similar solids, we're going to be, you'll see, so they're the 3D objects, yeah? And you'll see we'll probably most likely with an object, we'll be talking about, say, we'll use the area ratio to talk about things like total surface area. And then we'd be using we're going to look at the volume ratio. So this is going to be new. And that's when we would obviously look at volumes of the objects. Okay, so we can, we're just going to have a look at these objects. So when they'll tell you generally that the two objects are similar. So you can see here they've told me the two solids are similar. So what we're going to do is we're just going to have a look at these two objects. So I'm going to call this one the old object and this one the new, okay? So if we're going to get the length ratio, which is the scale factor, so if we're going to get the length ratio, so we'll call that K, or the scale factor. So remember we say new over old. So if we looked at this object, I'm going to call, you have to compare like the similar side. So I'm going to pick the long side of the box here, a length, and I'll compare it with the long side on the smaller object. So we've got the new one is 3 and the old one was 9. So we must simplify that, yeah? So we need to simplify. So we'll simplify that and that would become 1 over 3. So that the second object in terms of length and things like that is shorter is 1/3 of the original one in length. So then we learnt, the other day, we also talked about the area ratio. And we said that's when you square the K value. So in this instant, it would be 1 squared over 3 squared. So remember, you've got to use that simplified one. So that would be 1 over 9. So let's just have a look at that. So say I was finding the area of the face of this front of the box compared to the front of that box. So when I compare those areas, I should get the same ratio as I do there. I should get 1 over 9. So let's have a look. If you had, I'm going to use the small box, which is a 1 by 3, and because I'm going to do the area, and I've got the larger one, which is a 9 by 3. So what's 1 by 3 is? 1 times 3 is 3, and 3 times 9 is 27. So if you simplify that, you see we get 1/9. We do get that area ratio, don't we? Yeah? So we know we can use that. It will work out. So even if you found the whole total surface area, the whole total surface area will be, of the new object, will be 1/9 of the original. So sometimes they give us one and we have to work out the other. Now the last one we're going to look at is volume ratio. So who's going to have a guess? What do you think you have to do to the K value if you're trying to find the volume ratio? Cube it, yeah? Good, so you cube it. So in this example, it'll be 1 cubed over 3 cubed. So remember, we always go back to the length ratio, and we're using that. So that will equal 1 over 27. So if we compared I'm going to compare our volumes just to prove. So if I compare the volumes, so what I'm going to do is volume of the small box over the volume of the large box. So remember, we find volume by going length times width times height. So this one would be 1 times 3 times 2 over the other one, which will be 3 times 9 times 6. So you end up with 6 over, what is that? Ends up being 162, and that would simplify to 1 over 27. So that's good. That just shows that it does work for if we can just go to our volume ratio, and it does work because we've proved it there. All right, so this last little note down here is just explaining what we've already worked out. We know that the volume scale factor is cubing the normal length scale factor. All right, so here we've got a couple of shapes, and we're going to find the different ratios for the objects. So if I was asked for the length ratio for this one, okay, so we're going to call this side, I'll call this side the old and this the new. Okay, so if we're just finding a length ratio, just pick a similar thing. So I'm going to pick the radius, okay, a similar side or measurement. So I'm going to say the new so the new one is, it's always new over old. So we're going to say 1 over 2. So that cylinder in height is half the height of the big one there. Now, if we have to go to the area ratio, so if we were talking about, say, their surface area, because surface area is an area. So all I have to do is square that first one, yeah? So I can say a quarter. So the surface area of that, the little one, is 1/4 of the surface area of the big one. So say this big one had a surface area of 100, what would the surface area of the small one be? 25. Good. We're saying a quarter. Okay, so and then the last one, if we want to go find the volume ratio, we're going to cube the original one, the length one. So, sorry, that's 8. So 1/8. So the little cylinder is 1/8 of the volume of the big one. All right, so let's do the same thing over here. So you call the first one they give you the old one, and the second one the new one, and that's going to make it easier for you. So you go, all right, length ratio. We're going to say, I'm going to pick the side, the height, okay? So I'm picking the same dimension. So I'm going to say 5 over 20, but we need to make sure we simplify that. So what's that? 1 over 4, okay? Because this, so we need to make sure, maybe write that down, that we have simplified. Now, if you remember on your calculators, if you type this one into your calculator and press enter, it will make it 1/4. So in case like this number's easy, but when you get a few numbers that you don't sort of recognize, just pop it in like that. All right, so if we go to find, the area ratio, all we have to do is square that length one. So it'd be 1 over 16. And if we need the volume ratio, so we need to work these out because we're going to need them to solve some questions. So if we need the volume ratio, we're simply going to cube the original. So 1 times 1 times 1 is 1, and 4 times 4 times 4 is 64. So here's a question. So it says 2 solids are similar. So that's important. Once you see that word similar, you know you'll be using some of those. You have to use the ratios in some way. Okay, such that the larger one has its dimensions that are 3 times that of the smaller one. When they say dimensions, you might want to write up that means a length, okay? So if they say the length one is 3 times, so sometimes it can help just to draw a little diagram. So I'm going to say, all right, I had a little cube, and then I had a larger one because they said one was bigger than the other. So we're doing that. So if they say 1 is 3 times, just put 1 on this little one, and then that means 3 is on the next one, okay? So that you've got a bit of a visual and you understand. So it says how many times larger is the solid's volume. So we need to use this length ratio and get to the volume ratio. So if we write out our length ratio for this, because they don't tell us what the object is. I just made up a square. So we don't really know what the object is. So, but we can work out its length ratio. We can say it's 3 to 1, yeah? We'll call this one the old, this one the new, okay? So, because they said how much times larger is the bigger one. So if we can go straight to our volume ratio. And what do we need to do if we're getting that one? Yeah, the cube it. That means power of 3. So if we do that, 3 cubed is actually 27 and 1 cubed is 1. So how much times bigger is it? Yeah, so we go there for the solid is 27 times larger than the smaller, yeah, the large solid or whatever. Okay? Okay, so it says the 2 cones below are similar. So once again, we know that they're similar. So hopefully you see that word and you go, right, we must be using these ratios that we've learned about. Okay, and it said the volume of the smaller cone is this. So you actually know what the volume of this cone is. They told you. They said 120 centimetres cubed. Now it said find the larger cone. So it's volume, the volume of the larger cone. So this is the question. I've got to find the larger volume of the cone. Now, because they said they're similar, what we can say is if you do their volume ratio, so that means if you do the volume ratio where you've got the new over the old, so what it would be is K cubed, yeah? If you do that, that's going to, so if I'll just call it K cubed, that's going to actually equal the volume of, now if we call this one, I'm going to call this one the old and this one the new. So it's going to equal the volume of the new over the volume of the old. Okay, so what we're going to do is we're going to get that, first we'll get that volume ratio. So to get the volume ratio, we need to find the length. So let's find the length. So the length ratio we can use because they've given, we can find, because they gave us what? They gave us the radius. So we'll use that. So we're going to go new over old. So the length ratio would be 6 over 4. So remember, we have to simplify that. So what would that be?
3 over 2.
Good, 3 over 2. So this is essentially K. So if I want to find the volume ratio, what I've got to do is I've got to cube those numbers. We've had at the last few ones, it's always been a 1. Now on the bottom or somewhere. Now this one's got a 2. Doesn't matter, you do the same. So 3 cubed is actually 27 and 2 cubed is actually 8. Okay, so what we're going to do, this is pretty much K cubed, we've found that. So what I'm going to bring that up here into what we know we need to do. So I've got 27 over 8 needs to equal, now the volume of the new one, that's what I'm trying to find out. So I'll just call it X, and then we do volume over volume of the small one or the old one, which we actually know. Okay, so now that we've got that like there, what do you think we do? Good, we do solve. So once we set up some equation with an unknown, we can always use our solve function. So when you do that, you get X equals 405. So I can now answer my question. Therefore, volume of the large cone equals 405 centimetres cubed.